Good evening, ladies and gentlemen. We are glad to see so many enthusiastic participants joining our webinar today. I'm Nimashi Fernando, the Seminar Secretary of the Sri Lanka Energy Managers Association, and I warmly welcome you to our 66th Energy Management Forum, which is titled Solar Rooftop Power, Is it a Problem or the Solution? This EMF will be conducted by Mr. Prabath Premathilake, who is also an electrical engineer, planning and development of the Distribution Division D3 of the Ceylon Electricity Board. Mr. Premathilake graduated from the Faculty of Engineering, University of Ruhuna in 2010. He started his career by joining a solar company in 2011 as an electrical engineer. He engaged in solar PV system design, installation, commissioning, and in the provision of after-sales services. Subsequently, in 2015, he joined the Ceylon Electricity Board as a divisional planning engineer. He served in various capacities in solar-related committees and studies. He is also a member of the Solar Advisory Committee of the Ceylon Electricity Board and is involved in design and installation of solar PV systems in many CEB buildings. So without further ado, I cordially invite Mr. Prabath Premathilake to conduct his presentation. Audience, if you do have any questions, please drop them into the Q&A chat box, and we would also provide you the opportunity to use the raise hand option during the Q&A session, permitting that there is time for it. And Mr. Premathilake, the floor is on to you, sir, to conduct your presentation. Thank you.
Yeah, very old concepts, and we all know. But in 2016, with the collaboration of the Ministry of Power and Energy, there's a project, Surya Bal Sangramya. In 2016, it was introduced. Collaboration was Sustainable Energy Authority, Ceylon Electricity Board, LECO, PUCs, whatever the stockholders in that time. In this 2016 Surya Bal Sangramya, in addition to that net energy metering, there were two new schemes introduced, Net Plus and Net Accounting. Up to in 2016, as a cabinet paper, it is clearly mentions that this Surya Bal Sangramya is introduced to set off their own consumption, so sell electricity by solar PV systems by installing their own roof. But in 2022, this little bit developed, that there were few discussions that we have many abandoned rooftops, many large-scale warehouses, and the solar PV installations was limited due to their contract demand because their consumption is less. So there's a new concept. Can we allow rooftop solar PV installations, such kind of abundant roof, to get some more energy, some more rooftop energy to the network? As a result, in 2022, as per the instructions of the Ministry of Power and Energy, to maximize the use of available rooftops, available abundant rooftops, this net plus in CEB, net plus extra in the LECO scheme was introduced. So far, these are the four schemes that the interconnection, that any kind of solar PV system can be connected with the utility. So with these four schemes, these are the latest details that we are in the 2025 April month. These details are updated as a March 31st LECO details and the CEB so far up to date. That we have surpassed that actually around 106,000 solar PV installations, solar PV connections, and as a capacity around 1,581. This data actually, the LECO data is updated as per the March 31st, but CB data is as per the today data. In addition to that, all together, actually, let me come back to this slide again. As a rooftop solar PV penetrations, we have around 1.58, around 1.6 megawatt solar solar PV, rooftop solar PV penetrations. In addition to that, we have around 170 to 180 ground-mounted solar PV system. Altogether, it's around 1.75 megawatt rooftop solar PV capacities are installed in our network. But as a capacity, 1.75 is not a big number. But as a percentage, it is high. This graph I obtained from the World Data Organizations that just what are the percentage, the low carbon electricity percentage in the countries. I selected some specific countries, whatever our surrounding countries, India, Sri Lanka, Pakistan, Bangladesh, and also as Asia average. And also I didn't select the Bhutan and Nepal because we know that they are very rich with the hydropower plant. And also UK, whatever this that. Actually, you can see in Sri Lanka, where we are, around 50% we are in the low carbon electricity generated the country. In addition to that, I wanted to show you some important data. One of the important data. As I explained, up to 2022-21, only net metering, net accounting, net plus capacities for the schemes were there. Up to 21, our one of the famous solar PV capacity is 5 kilowatt, 5 to 10 kilowatt. So in the 5 to 10 kilowatt, actually, so far, actually I used only CB data. I didn't find the LECO data. I find the CB data since it's available with us. Since 5 to 10 kilowatt capacity range, we have installed around 214, more than 200 megawatt. And also 10 to 20 kilowatt range, we have more than 250, 275 megawatt. And 40 to 100, also again, more than 250 megawatts. So altogether, by looking this data, the majority of our solar PV penetrations are less than 100 kilowatt capacity. Less than 100 kilowatt capacity. That's one of the data I wanted to share with you. These are the distributions, the graphical representative. And in addition to that, I wanted to show one another graph that prepared by our system control center. That's the weekly demand curve variations from 2021 to 2025. The Monday, Tuesday, Wednesday, Thursday, Friday, and Saturday. But I wanted to show only this graph that in 2025, our day demand, system control, this day demand is getting lower in 2025. That's one of challenges we are facing. So due to this high penetrations, what is the biggest challenge that we are having now? The biggest challenge, one of the biggest challenge is the voltage. That we know our LV distribution network is not designed to host solar PV system. We know that normally our distribution network, the LV line length is more than 1 kilometers. Likewise, our distribution network is not designed. So what happened is, if we consider this as our LV distribution line, this is a transformer, this is a bus, and this is a line impedance, and this is some kind of customer point bus of customer. And we say customer load, active power load as a PL and reactive power as a QL, and also some kind of a capacitance as well. At this moment, what happened? When a solar PV system is connected to this bus, actually for the moment, we are not giving any reactive power support, but we are giving only the active power for the LV network. What happened is, as per these equations, our supply end voltage plus something is always in the common coupling point voltage. So in the PG minus PL mean, whatever the active power generations minus consumption will impact the common coupling point voltage. As per the current context in Sri Lanka, that most of the net metering and net accounting consumers, they are installed a higher capacity solar PV system. In the daytime, they are what they do is in the daytime, they use as a CB network or utility network as a storage, and they will feed to the network. So PL almost is minimum or maybe zero. So the voltage is increasing. These are some kind of a measurements we obtain that up to around 9 a.m. Normally the voltage in 3 phases are in the same situation similarly in the bands as well. But after 9, after 10, the phase voltage are varying very differently. Actually, not very differently, but it's depend on the generations. You can see some phases are increasing, some phases are reducing. If there's any single phase solar PV system, that the phase voltage is increasing. Likewise, this is the first biggest challenge in the LV network that we are facing at the moment. The next one, up to the last year, the prevailing grid interconnection standards in Sri Lanka actually requested PV system to disconnect at some kind of a disturbance, voltage disturbance or frequency disturbance. So what happened when there's a fault or maybe generator tripping, there's some kind of a disturbance, voltage disturbance, frequency disturbance. If the solar PV generations are disconnected simultaneously, again we have a generation drop, and that can be improve the situations. Actually, the worsen of the situations. Even solar PV systems are connected, and if there's any disturbance, if the solar PV system are disconnected simultaneously, again there's a challenge. In addition to that, when they're after an outage, if the solar PV systems, all solar PV systems are ramping up simultaneously, again there is a challenge for the grid. So I wanted to highlight up to here, there's some kind of a challenge to balance the demand and supply if there is some kind of a situation, if there's some kind of an event. So what kind of solutions we have? Actually, I'm talking here about the solar PV system. At the moment, this was not a big issue in other countries as well. This kind of similar situations happen in everywhere. They have learned, they have tested, they have learned a lot of things. Then accordingly, there were some kind of a standards, interconnection standard, and also inverter standards they have to adhere. Normally, whatever the inverters available here today, that can be a part of a solutions. That can be a challenge, but with the challenge that can be a part of a solutions. So what we need is here, we have to get the support. We have to get involved whatever the inverters in our network. As I have shown you, around 1,750 megawatt solar PV inverter capacities are in our network. If they can provide a solution, if they can provide the support for the stability issue and voltage issues, yes, we have to take it. The first solutions, actually, we all know, as I explained, the biggest challenge at the LV network is the voltage issue. That we have solutions, voltage regulation operational strategies. Actually, we called as voltage control mode supports. These are two very famous supports: voltage reactive power, volt bar control, and the volt watt control. what happens is if the voltage is in the normal range, we don't request any kind of reactive power support. But if the voltage is high, we are requesting the inverter to absorb the additional reactive power and get the voltage to the back to normal situation. If the voltage is less, we are requesting inverter to absorb reactive power and come to the normal situations. In the active power, we say if the voltage is beyond our permissible level, you have to curtail the active power and come to the normal operation voltage. These two are very famous, but unfortunately in the LV network, we are yet to be implemented. This one we didn't implement yet. We have to implement as soon as possible this voltage regulation operation strategies. These not only these, actually these are the two very famous voltage control regulation operation strategies. In addition to this, there are few more options. First one, constant power factor control mode. That's also some kind of a voltage regulation operation strategies. For the moment, we operate in the constant power factor control mode, but in the unity power factor. We are not requesting any reactive power support. In these situations, whether how much sunlight or how the electricity demand changes, we can set a fixed power factor and we can ask inverter to operate. Then the inverter is always try to keep a steady balance between the actual power and the total power it handles. That's also another good options of the voltage regulation operation strategies. There are another one, constant reactive power control mode, whatever we can fix a control reactive power amount and we can control the voltage in the network. And also there's another system called active power reactive power control mode that we call Rooftop control mode. That's another voltage regulation operation strategies. On behalf of these 5 voltage regulation operation strategies, we can have some kind of a combinations. If we use volt-watt control mode, we can use volt-watt control mode in simultaneous. If we use constant reactive power control mode, we can use volt-watt control mode. Likewise, we can use some kind of combinations to control our voltage in our network. That is come with our inverters. Next one, when we have some kind of a disturbance, in our network, voltage disturbance or frequency disturbance, I informed you, I explained you that so far we wanted to disconnect the solar PV system from the network. But there's an opportunity, there's a facility to connect the solar PV system and get the support out of it. When we talk about this right-through capabilities in the abnormal operations, the inverter normally will go around few control mode operations. I highlighted this one is a cease to energize mode. That's in the yellow color. That's a cease to energize mode. Cease to energize mode means that the synchronization with the local electrical power system is there, but it will not inject any power to the network. Once the system is recovered, it can inject the power, maybe 80%, maybe 90%, or some significant portion of the power generated before the event. That's we call cease to energize. And permissive operations, that's also another operation mode. In a permissive operation mode as well, that it will maintain the synchronization with the network. But as per the utility requirement, it can inject the power or it can cease to energize. That's a utility decide. In the mandatory sessions, in the mandatory operation mode, what happens is It need to maintain the synchronism. It need to inject the power, and also it need to in situations, in some situation, if the system is forced to disconnect, how their power is again come to the that we call enter to the what we call enter the service. There are some conditions they have to follow, and likewise, this in the voltage disturbance ride through facility, the voltages are shown in here. Voltage are shown in here. The more important is in the voltage, we can define this range 0.88 to 1.1. Likewise, we can define as per our available guideline. At that guideline, at that range, solar PV inverter shall operate in continuously. It is in the normal operation mode. If the voltage is below this value and some certain margin, there is some kind of a mandatory operations that we have to maintain synchronism. We have to inject the power, and also what we call in this operation mode, in any time, the generator will not trip. In this operation, the generator will not trip. So what happened? Let me explain with our LVRT curve we used in the grid connection code. This is the LVRT curve we use in the grid connection code. If there's any kind of a voltage disturbance, let's say around 50% disturbance, voltage dip is here, that is this value. And up to this value, this seconds, the voltage, the inverter will not trip. The volt up to this time, maybe around 1 second, 0.8 second, inverter will not trip. Instead of trip, actually we can ask the inverter to operate one of this operation mode. Maybe mandatory operations. It should continue the reactive power support. It should inject the active power. Or maybe we can ask them to cease to energize. And if the disturbance is over and voltage is recovered, they can inject the whatever the power before the event. Likewise, we can ask the inverter to support in a disturbance event. This is in the grid connections code, and also in very in the inverter settings that very recently published by the Sri Lanka Electricity Board. This is the low voltage LVRT curve we follow. Similar to the LVRT low voltage side, there's another options to have a high voltage right through as well. Similarly, if there's any kind of a switching of a large load, maybe energizing a capacitor bank or any fault, the voltage can increase in very suddenly in millisecond wise. Then inverter can be able to ride through in the such kind of conditions without tripping. What happens is when the tripping is there's some kind of a reconnection delays as well, enter to service delay as well. Then these situations can worsen our network stability. But if we are able to operate, or maybe inverter to ask them to switch the facility of the LVRT and HVRT, that they will connect to the network and they will give the support at some kind of a voltage disturbance. As I explained, that there's a percentage, there's some capability, inverter capabilities. Let's say in some situations, we may have some kind of a consecutive disturbances, few consecutive disturbances, but as per the inverter capabilities, and also in latest standard, it has defined actually how many number of disturbance they can support. That facility is available. They can ride through few disturbances, and they can manage our network in such kind of a voltage disturbance. In addition to that, there's another important feature, grid support feature called dynamic voltage support capabilities. When the active power, when there's any kind of some kind of an event or some kind of after an event, once the solar PV generations are starting, they can follow this kind of a dynamic voltage support functions. They will balance enables in order to provide rapid exchange of the reactive power. They can balance with the increment of the voltage. This is the amount of power or reactive power voltage support we can give. As mentioned here, the PV inverter can inject minimum 2% of the rated current per 1% of voltage drop. But there's a dead band. Of course, we know that from 0.9 to 1.1%, it is a dead band. We don't need any kind of a support. Beyond this point, if the voltage is dropped by 1%, they can inject minimum 2% of reactive power. If the voltage is increased by 1%, they can consume reactive power by 1% or 2%. Likewise, we can define dynamic voltage support capabilities in the inverter itself. So in these situations, if we need to have some kind of reactive power, that inverter can support. In addition to that, so far I discussed about the voltage disturbance. Here, there's a facility to frequency disturbance. When the frequency is not in the normal operations, it is likewise some kind of a, let's say, when one of our generation is disconnected, the frequency will drop. But at that situation, if the inverter also disconnected, that situation, of course, will worsen. Therefore, in that situations, the inverter must remain connected. Inverter must remain connected. But when the frequency is increasing, it can be disconnected from the grid. Actually, instead of disconnecting and connecting, it can keep connecting and ride through the frequency disturbance. What happens is, everyone is discussing, this is one of our topic that discussing, can we do this frequency ride through with the grid following inverters? Can we do this frequency disturbance ride through with the grid following inverters? Yes, we can. At some part, actually up to the some certain level, this can be done. As explained here, I explained that inverter has some kind of operation mode, mandatory operations, continuous operations. Likewise, similarly, we can define from 48.8 to 51.2, that's a normal operation range. We don't need some kind of a frequency right through. But if the frequency is dropping, frequency value is dropping more than the 48.8 and in between 47, the inverter should continually connected to the network and should support for the frequency right through up to 300 seconds. If the frequency is less than 47, no ride through requirement, but inverter should be connected up to 0.16. If the frequency is drop more than 47, more than 160 milliseconds, inverter can trip and isolate from the network. Likewise, similarly in the upper side as well. If the frequency is more than 42, we don't need to ride through facility, but up to 160 milliseconds, inverter shall be connected. From 51.2 to 48.8, the inverter need to be connected with the network. It should provide the support to ride through. And next one, Another disturbance right through is the voltage phase angle. That in the single phase and three phase inverters, that up to 20 electrical degrees, it can ride through for the single phase in a sub cycle to cycle unit frame time frame. If the voltage is less than or equal to 20 electrical degrees, it can ride, it have the ride through capabilities. And even in the single phase inverters, also shall remain in the operations for phase angle changes within the sub cycle to cycle time if the applicable voltage is less than or equal to 60 electrical degrees. This facility also available in the inverters. We can use if the voltage phase angle also changes due to some kind of a disturbance. In addition to that, voltage disturbance are there, frequency disturbance are there. And in addition to that, in some certain standards talk about the frequency variation, sustained operations for frequency variation. Likewise, I am going to explain how the frequency disturbance right through is happening here. When the frequency, when the system frequency is decreasing, when the frequency is decreasing, the inverter shall not reduce the power output in response to the decrease in frequency. Inverter shall not reduce power output if the frequency is reducing. But in these situations, our inverter may have operate in the power quality response mode. Maybe or maybe demand response mode. Power quality response means maybe we are in the constant power factor mode or maybe volt power mode. Likewise, whatever if the voltage, the active power available, even though active power is available, but we are in the some kind of power quality response mode. And also system frequency is decreasing. At that time, without it, they will disable the power quality response mode, volt wow, whatever the operation mode, constant power factor mode, and it will increase their power output linearly with the decrease of frequency up to the below the lower limit of the continuous operation frequency range is there, reached. If the system is operated in the some kind of power quality control mode, there is some kind of additional active power capabilities, and we are going to use that active power capabilities to increase the frequency when the frequency is going down in the system. And in other way, when the frequency is increased, that of course we have the active power capability, and we are reducing the power output linearly in the increase of frequency until the exceed the upper limit of the continuous operation range until the frequency of power output is minimum is reached. So likewise in the grid forming inverters also, we can easily respond in the increase in frequency, but in the decreased frequency, there should be the inverter should operate in the power quality response mode. If the inverter is operated in the power quality response mode or any kind of a demand response mode as per system control center, they will stop that power quality response mode or demand response mode, and they will inject the power output linearly until the frequency is reached to the minimum lower of the continuous operation frequency. Likewise, inverter can itself ride through in the frequency disturbance as well. So those are the two challenges, and those are some kind of solutions in built in itself in the inverter. So what is the most important thing? These grid support functions are available in the each and every inverter model, because these inverters are not only manufactured into the Sri Lanka, but it is manufactured into the international market. These grid support functions, even though very new to the Sri Lanka, but it is not for the other countries. Even Spain, even German, even Australia, everywhere they will use these grid support functions. But once we are introducing this kind of feature to our network, our Sri Lankan market, normally manufacturers will provide some kind of a country-specific operation profiles. Since we are not requesting this LVRT, or maybe 10-minute volt sustained operation voltage tripping, or maybe frequency group characteristic, for the moment, it may not be available with the Sri Lankan grid code. That's what I mentioned is Sri Lankan grid code mean the inverter operation profiles for the Sri Lankan market. It may not be available. But firmware modification easily can be done because each and every inverters are for the international market, for the international standard, IEEE standard, Australian standard. Each and every inverter manufacturing and with the capabilities of this kind of a grid support functions. But when we ask into the implementations, what is the most important thing is this firmware modifications sometimes we may require. In firmware modifications, the inverter supplier and whoever our inverter installation in Sri Lanka, they have to discuss and get this facility. That will take some time. First one. Second one, whatever I explain the voltage support facilities, some part of the generations will impact to the customers, end of the day, customers' generations. Some part, but almost all the researchers, almost all the studies shown that instead of having the voltage control support, if you use the tripping facility, that's what I explained was earlier, the grid standard were not requested to support at the voltage increment or voltage reduction. We didn't request any support. We asked them to disconnect. Now we are requested to travel right through some kind of a volt-var mode or volt mode. In that situation, there is some kind of an advantage. There's an additional generation rather than tripping it. So as stakeholders in this country, we have to sit together, all stakeholders. Who are the stakeholders? Inverter manufacturers or representative of the inverter manufacturers, solar PV service providers, utilities, regulators, Sustainable Authority, PUCSL, and we have to study what are the most potential, most beneficial grid support functions we should enable in our inverter. And it will take some time. What are the action plan, time plan? In these situations, let's say we will get a decision. Our each and every inverter shall be some kind of a smart inverters from this point. And each and every our inverter shall have some kind of LVRT facility from this point. Likewise, some kind of action plans we need. Because so far, we are not getting a voltage control mode support, volt support. Neither of discussed grid support functions we are not getting from our low voltage network. So, as a stakeholders, we all have some kind of a responsibility to sit together and have some kind of a action plan to implement these grid support functions as soon as possible. In addition to that, for the long term that we all know, we all discuss, we have to enhance the utility network. We have to increase the grid flexibility, incorporating some kind of a storage, pump hydro, or maybe some kind of base or some kind of a grid flexibility we have to improve. Then also we have to improve the visibility and forecasting. I considered as my point, these can treated as some kind of a long-term solutions because it needs some kind of a time, but also as well as some kind of a cost. But So far, we have around 1,750 megawatt inverter capacities, inverter capabilities. If we can have some kind of a reactive power support, voltage control mode support from this 1,750, we can easily get the support as a short term. That's why I differentiate this as a long term and short term. So these are the end. This is end of my presentations, and I hope I had covered what I expect to cover today. And thank you for joining us. And if you have any kind of questions, we can ask. Ms. Bimasha, I think, hope you are available there.
Yes, yes. Thank you, Mr. Premathilake. It was a very insightful presentation indeed. And audience, I am sure you have many interesting questions for him. So let us now move to the Q&A session. This session will be moderated by our past president, Mr. Harsha Wickramasinghe. Mr. Wickramasinghe, the floor is open to you, sir.
Good evening, everyone. So you can raise hands if you have any questions. Just to get the ball rolling, I have a question. I will start off with the likely total hosting capacity. Now, if we take the entire generation, the fleet of generators we have in the national grid, it's coming to something like 5,700 megawatts or somewhere there. So out of which about 1,600 is rooftops, and further 200 is about ground-mounted solar, if I'm not mistaken. So
Yes.
how much more we can go with the solar rooftop? What is the likely hosting capacity we are discussing well into the future, say till next 10 years? Any indication?
Yeah, actually, that part need to be evaluated with considering the latest development as well, the stability issues and the network capacities as well. But the major issues I noted in this situation is actually not the network capability, but we don't have a load. We don't have a load. Therefore, whatever our local generation if consumed, that we don't have in such kind of issue. But as per the last few years, our daytime load is reducing, and with the development of our the interconnection schemes, so there's some kind of issues, that kind of a challenge with the integration schemes. Almost all the peoples, almost all them are trying to generate and export, not a consumption, or maybe not a storage. But for the moment, I cannot give you some kind of a ballpark figure about the hosting capacity. But with considering everything, network capability, actually not capability, that development of the loads and stability issues that we have to study. Actually, I cannot give you some kind of a ballpark figure for the moment.
Okay, thank you. And we have a raised hand from Mr. Shavindranath Fernando. Just a moment. Yes, Mr. Fernando, you can speak up. Mr. Fernando?
Oh, I have to unmute myself.
Yes,
So
we
I'm
can hear you.
happy that Engineer Prabath, CB engineer, has come out very boldly to speak about the reality that the national grid is facing. As very correctly he mentioned, there is a huge problem of what is said by lack of load. What it really means is that during the time periods, there's so much of generation, more work, and there are certain must-run plants, not only for the inertia, but also for other purposes. And so this is juggling process right now, or the system is doing it by itself. I mean, people might say that the system that they should be not be sleeping, all kinds of things they can say. Is way beyond any human control. I think it's understood by everybody who is in this audience. Then the policy matters. We cannot deny the fact. Whoever announced that policy, the policy has been ingrained into the population. The engineers, humans, producers, vendors, whatever the stakeholders, including the normal man on the street who expects by solar intervention or renewable intervention in the broadness, the tariff will come down. So we are in a bit of a jam, I would say. That has many flavors. Bitter, sweet, sour, some may be poisonous, some is very sweet. So this has to be discussed very openly, very frankly, unbiased, and in rational manner. I'm very happy that people like Prabath and also other people in CV are very much aware of this situation. But it has to be hand managed. Now, the mere fact that what happened during the New Year is being criticized heavily. Nobody understands. So we have to talk in a sense exactly what Prabath said in a common man's language. And he said something extremely important, which I will support with both hands raised. Let's get down to talking. All the stakeholders, prosumers, consumers, solar vendors, inverter vendors, at least in a shorter period, we must immediately get into a cooperative mode than adversary mode and ask them to support the grid, at least on this transient stability issues, falls, and also during certain high sunny, low demanding areas. Of course, all what he said cannot answer all the problems that we are having. But at least some of the problems, like what happened on the that very disturbing day in February or March, I can't remember. Some people say March 9th of February, right? Whatever the date may be. That kind of situation could have been at least smoother to a certain extent. Of course, I will not blame anybody. These are learning curves. So learn and learn fast. I only can wish people like Prabath plus all the other engineers around him and his superiors, right up to the chairman, to take this very seriously, including the system development. They have also come up with certain suggestions. It's best that we address this sooner than later, not days, in minutes and hours. Right? Sooner we do, the better. Thank you very much.
Thank you.
Thank you, Mr. Fernando. Mr. Prabath, is there any response to Mr. Shavinath Fernando's comment?
Yeah, actually, I think he's our former GM, and I worked with him last few months. I think I completely agree with his idea. No additional comments actually.
Okay, thank you. Any other questions from the audience or comments?
Mr. Vikramasinghe, there is one question in the Q&A chat box.
Let me first handle Dr. Amila Vikramasinghe. Dr. Amila, you can speak up.
Thank you, Mr. Vikramasinghe. Hope I'm audible. And first, I should thank the presenter, Mr. Prabath Premathilake, about the excellent presentation he had done, and also thank him for the positive kind of approach he has taken in identifying how kind of a problem can be made a solution, even because we all know that future will be renewable, but then how we all can get together and find a solution for those so-called problems is the way forward, without totally being opposed to the development. And I see that that also can be done and will be done only by the people who are capable of doing that. So only solution we have is people like Mr. Premathilake, looking into this, because otherwise, as Mr. Shafi Fernando mentioned, being adversaries of these technologies is not going to help. We have to be part of the supporters as well, because otherwise the so-called supporters will never come up with this kind of progressive or constructive contributions, but we'll try to squeeze in whatever possible capacities without helping the system at all. So I think even for the CEB, for the betterment of the system stability, should have people like Mr. Premathilake working on identifying these kind of inherent issues, as well as technical solutions that the other countries are coming up with. So that is my first comment, but I have a question related to one of the slides, or one of the comments Mr. Premathilake mentioned, that is about these even existing inverters being capable of providing these kind of support, given a firmware update is provided. So can we kind of seriously think about this? I'm not sure to what extent all these capabilities will be available with the models we have in Sri Lanka, but kind of a survey. This is not going to be difficult, because the SCA knows all the inverter models we have brought down, even the numbers they will know. So it should be very simple for either CEB or SCA to contact or reach out to the suppliers and see realistically whether these can be done with the grid code change or without it, to what extent we can get the support of existing inverters to provide this grid support functionality. So this can be done, I think, without much effort and without much external support, because we have the data. So why not do it immediately and see at least the voltage price issue can be managed by maybe incorporating a small, whatever the firmware update, or maybe just a change in the setting. So if that can be done, why not do it immediately? Because this can be done without much cost or effort. What do you think, Mr. Premathilake? Thank you.
Yeah, Doctor. Actually, last few months, last few weeks, I was involved in some kind of discussion with the inverter manufacturers as well. And as you said, that yes, of course, we have to do some kind of a survey, but as per their comments, that normally this grid support functions, even though very new to us, but it is actually it is tested, and they have corrected whatever the issues in this kind of grid support functions in other countries. Therefore, we are not in a test bench for the moment now. They have learned the lessons and they have corrected some issues. Therefore, I think better do some kind of survey, of course. But with the inverter manufacturers, as per the discussion with them, I think most of the inverters are capable. They have expressed that situations. But the situation is that if we are finding some kind of a technical solution, there is some kind of a compensations as well. So So when providing some kind of a solutions, we as I mentioned in the end of the presentations, sustainable energy authorities, inverter suppliers, and also inverter installers, we have to get together and find the solutions. We can give some kind of regulations. You should implement this kind of inverter settings. We can give some kind of regulations, and also as for the information that we are in the step of revising the embedded with code, embedded connections code as well, and we are trying to incorporate all such kind of technical facilities with support facilities to the inverters. But at the end of the day, this will work out if we work together.
Thank you, Mr. Premathilake. There's one question in the Q&A. I will read it out. Why CEB? The question is by Mr. Rukshan Jaisingha. Why CEB not go into capturing the rooftop solar generation to have an exact load curve? And did frequency control load shedding will upgrade with the generation upgrade in the future?
Actually, this is in the steps in the process stage. Actually, we also, I think, with the support of Sustainable Energy Authority, also we in the getting the details, capturing the rooftop solar PV generation to the exact load curve, and as I explained, around 100,000 solar PV installations in the market at the moment. So we may not be able to capturing each and every one, but we are in the process. We are in the committees. There are some committees work on this kind of situations. They are trying to get their generations curve and get to actually incorporate with the exact load curve. And frequency control load settings, actually that also will be updated. Actually, I'm not much aware about this, the load frequency control load setting. Actually, if there is someone in the system control center, they can share actually. But as I heard that there's some kind of upgrading process as well.
Oh, thank you, Mr. Premathilake. I see the raised hands of Mr. Ronald Commister. Mr. Commister, past president of SLEMA. Please ask your question.
Yes. Am I audible?
Yes, we can hear you.
Yeah. Mr. Prabath, my question is, if all agreed to change the inverter settings, my question is it possible the manufacturer to do the changes centrally, or else do we have to go individual for each and every individual household? That's my question, please. Whether we can change centrally or not.
Yeah, actually, the inverters are connected remotely, and they access they can access remotely. The firmware upgrade can be done in the remotely. But the issue is in some other some European like SMA, they are concerned about the Personal Data Protection Act that they are not willing to do in remotely, but they will provide some kind of firmware to upgrade in locally. They will not do as a lot, but they will provide some kind of firmware to upgrade in the locally. That can be done if all the solar PV inverters are connected in remotely.
I beg to add, once they give that option, then even CEB has to do at one central point, or do we have to go individual houses?
Inverter supplier will authorize to do some kind of operation for their authorized agent or distributor or installer, but CEB may not be able to do that, sir.
Okay, thank you. Got it. Thank you.
Any more questions from the audience? Okay, I think we have answered everything. After a busy day, I'll hand over the reins to our compeer, Ms. Nimashi Fernando.
Yes, Mr. Premathilake, thank you very much for fielding our questions. And Mr. Vikramasinghe, thank you again for moderating the session. So we would wind up the session for today. And the SLEMA looks forward to seeing you in another insightful EMF sooner or later. Until then, good night and thank you.